Welcome to part 2 of our condensation chapter lecture. So this is chapter 22. In part 1, we covered reactions between two carbonyls if one is an enolate and one is acting as our electrophile. In part 2, we're going to be talking again about enolates being nucleophiles, but instead of attacking just a straight carbonyl, they're going to be attacking a conjugated carbonyl. So, conjugated carbonyl, sometimes called alpha-beta unsaturated carbonyl, can be ketone, aldehyde. So alpha-beta, right, so this is your carbonyl, this is alpha, this is beta, and there's that unsaturation. That's why it's called alpha-beta unsaturated. Now, these are conjugated structures. They have resonance structures. Some resonance structures are better than others. Here are the four for this structure. Right, so you can split this double bond and put a minus and a plus here. So this would be how your typical carbonyl would act as an electrophile, with this carbon being electron deficient. But because this is in resonance now with this double bond, right, this double bond can come here and that charge moves to the end. And you can also split this molecule to straight here, and that gives you this kind of resonance structure. The point being that you have a site that is electrophilic at this carbon and a site that's electrophilic at this carbon here, right? So these are the electrophilic sites. So when you add a nucleophile, that nucleophile actually has a choice of where it will attack. If that nucleophile attacks the carbonyl directly, like this, then you get your acyl addition, and then possibly substitution. Of course, in this case, it's a ketone, so that would be addition. And when you quench, you get your addition product, and the unsaturation remains unchanged. If the nucleophile instead attacks at this carbon here, that double bond moves that way, and then your product actually looks like this. Right now, and this negative charge is in resonance with the carbonyl, which is what stabilizes it. So you get this this product that, when quenched, so it's important to note that this is the quenched product, not the enol, right? The ketone is this way is more, oh shoot, I forgot something, there we go. Yeah, so that this double bond moves here, and so this is your enol form, right? But this is, when it's quenched, this is the product that you're going to see. This is called conjugate addition product. It's also called 1,4 addition. It's called 1,4 because if you count from the oxygen, 1, 2, 3, 4, and you're adding on that 4 carbon. By simple addition, it's also called 1,2 addition because you're adding 1, 2. You're adding to at the 2 position of the carbonyl. Now, because you have these two possibilities, depending on your nucleophile, you will get a different ratio of either your simple addition product or your conjugate addition product. The main rule is that strong nucleophiles tend to give the simple addition as the major product. Strong nucleophiles here are anionic. So that's hydrides, right? Grignards fall into this category. Also, other anionic, we have nitriles and strong bases, right? These are considered strong anionic nucleophiles because they have that concentrated negative charge. They are better at attacking straight into the carbonyl. That's their preferred method. So you'll see some conjugate addition as well, but they're actually they prefer doing the simple addition. They attack that this carbon well. On the other hand, weak nucleophiles, quote unquote, tend to prefer conjugate addition, right? So weak nucleophiles, maybe better to call them weaker. They are neutral usually. So alcohols, water, amines, thiols, we saw all of these were like the weaker nucleophiles, and enolates, which is why we're discussing it now, right? So enolates are very good nucleophiles, and they're even, they have that negative charge, but because of their resonance stabilization, they prefer the conjugate addition. Oh, sorry. So this is a feature of enolates, and so if you're doing, all the aldol reactions, but one of your, electrophiles is a conjugated carbonyl, you're not gonna get the same reaction that you thought you would, right? You're going to see a lot of conjugate addition. So if you see this sort of conjugated alpha beta unsaturated carbonyl, you should know that this is probably going to do conjugate addition. So just an overview of simple versus 1,4. The main things, why the simple, this has a lower transition state, but the 1,4 is the lowest energy product. So it is favored by weak nucleophiles, and also in some cases, or very bulky nucleophiles that just can't get into the electrophile. So you might see cases of that. The main thing to remember basically is that the weak nucleophiles and your enolates like to attack here at this secondary, at this partially positive carbon, whereas strong nucleophiles prefer to attack directly here at the at this electron deficient carbonyl. So the Michael addition is just that. It is a reaction of an enolate with a conjugated carbonyl. Let's look at this mechanism. So in this case, our cyclohexanone, right, is going to get deprotonated by, this is a strong base, and form this enolate. Then the enolate will see our other electrophile, and will attack at this position, and that double bond will put the charge there. Like this. Now this negative charge is in conjugation here, but you can just show it quenching. So a second step will be to quench. You're going to need some proton source, and your final product is this one, like this. So, right, so first step, you're going to need a base to form your enolate, and second step, you will need to quench. Acidic conditions, usually, it's to provide a proton. Right, here's a two-part practice. Remember, try this at home. Obviously, where else would you try it? All right, what product is formed when each pair of compounds is treated with sodium hydroxide, sodium ethoxide in ethanol? So we have conjugated carbonyl, and they're giving us these really good enolates here. So first we're going to form our enolate. Oops. Right, so this is a most stable enolate, right, between two carbonyls. That alpha hydrogen was really acidic. And then this will react with, I'm going to just draw it this way, over here. And that'll be put a negative charge here that will get quenched. And my final product ketone stays, and right, that's it. Part B. Okay, so here, this is my conjugated carbonyl, and this is going to be my great site for a enolate. So first I'm going to make my enolate here, and then it will attack here. Negative charge that gets quenched. So this is untouched, and this adds to my enolate like that. Yeah. Okay, more practice. What starting materials are needed to prepare each compound using a Michael reaction? right? So we want to pick out where there could have been, who could have been an enolate and who could have been a conjugated ketone, right? So here between these two carbonyls, right, this would be a great spot to have put my enolate, and then so then I would break here, and this would be my ketone, right? So A plus right to this enolate like that. Now, could I have broken it up maybe a different way? The thing is, so then let's see. If I had broken it up, if I had said, okay, this is going to be my enolate, okay, so then I'm going to attack this conjugated carbonyl. That in theory works okay, but this is definitely not the best pairing, right? That's not the best spot to have. Basically, if you were comparing this enolate versus this enolate, if you were mixing these together, this is definitely going to form an enolate. This structure is going to be better at forming enolates. That's the more stable. So that's a better pick, basically. So I'll put in a little note here. Okay, so with B, again, so trying to find that enolate that's between two carbonyls, right? This is another ester here. So that would be better, and then we would break here, and this would have to be our double bond. So B, it's like this, plus that enolate. And C, this is a good enolate spot. We break there. That, and so this is CO2 ethyl, and then this is, oh, phenyl, like that. Right, so the trick to these is to find the best enolate. All right, the Robinson annulation is really cool. It's really just a combo Michael addition and then aldol, intramolecular aldol reaction. This is called a cascade reaction. And you want to be careful with the conditions that you use, right? Because basically the conditions you're using for the first step, like this base, then also promote the second step. So it's very hard if you are set up to do that. If your Michael addition sets you up for another aldol, it's very hard to stop that from happening, because you still have the base there. So in this example, right, we have a Michael addition happening first. We have an enolate being formed here, right? This is the more thermodynamic enolate. Because we have sodium hydroxide, it's going to attack here, and we get this addition product. But now this ketone can become the nucleophile. So when it was the conjugated ketone, it was the electrophile. now it's going to become the new nucleophile for my next reaction. So now it forms an enolate here that can attack this ketone. And in this case, they're showing the full condensation product, right? So they should have specified there will be heat here. Well, I should have specified. So without heat, you would stop at the aldol addition product. Which is this. Oh, this. Right, so this would be just aldol addition. Now, one thing you might have noticed right away, you're like, wait, no, this is a weaker base. I should be getting the thermodynamic enolate instead here, right, with this base. And you're right, you would, but this then would be much too small of a cycle, right? This would be 1, 2, 3, 4, four-membered ring that would be strained. These are reversible processes until you get to the condensation, right? So this would not be favorable. And so this would revert back, and eventually you would make the other enolate, and that would form a more stable ring, because this is 1, 2, 3, 4, 5, 6, right? And that's the 6-membered ring that's formed. So you're absolutely right that this is forming the wrong enolate, but it's forming both. It's just that the minor enolate product is actually making the major product, right? So you do actually form both enolates, and only this one gets used in the reaction. Your product in the end, if you want to identify a Robinson annulation product, the product always has a ring with an alpha beta unsaturated carbonyl. Okay, so if you see this this inside a ring, there's a good chance that it was made by a Robinson annulation reaction. Okay, here's a practice. We'll work through this one. We'll draw the whole mechanism for this. So again, here we have options for our base. We could deprotonate a few and make different nucleophiles, different enolates. But this is, these are the more acidic hydrogens, right? So this is definitely where our enolate will be formed. Let's make it. And it will attack here, right? So first step, is like this. Now this negative charge, so now this new enolate gets quenched depending on what you're using. In this case, the solvent is methanol. So it's going to steal a hydrogen from methanol, become this. Right, and form this base, right? So there's more base present. And that's why now we cannot really stop the next step. The next step, we have another base here, and it's seeing these protons, and now these protons are fairly acidic. Now, yes, right, there's still a proton here, and that will get deprotonated as well, but this would not make a, this is not going to do the Robinson annulation, so we're just going to focus on what happens if you form this enolate. The aldehyde, right? And now if this enolate comes in and attacks our aldehyde, what's our ring size? 1, 2, 3, 4, 5, 6. That's definitely a favored ring size, so that will happen. I just draw a 6-membered ring and label it right off the bat. 1, 2, 3, 4, 5, 6. So 6, we have our oxygen from the aldehyde. At 4, we had a methyl group. At 3, we have ester. And at 2, we had our ketone. Right? And then we need to quench this as a final step. Right, so that would become the alcohol. Now, if there is heat, then condensation. And so if we got condensation, then the final product would be this one with the ester. There you go. So that is a full Robinson annulation with condensation. So all that's left are some book problems. And that's the end of chapter 22. We'll go over, I will post the answers to these problems in the slides, and then we can go over them during Zoom time as you guys want. Okay, thank you.